CSE 310 in fall 2021. Now, originally this problem came from, was what is called the Königsberg Bridge problem. The city of Königsberg, which was in Prussia at the time, had this river that went around an island. So this is an island in the city. And the city had this part labeled X to the north of the island, a part to the east, and a part to the south. And you can see that there were, so these are, I can draw really well. So these are really fancy bridges that go from the island to the north, the island to the south, and from this part to the north to this part to the east, and similarly for the south. Now, at the time, people were wondering, could they start somewhere at home and go over all of the bridges and come back to home? And this problem got modeled in this form as a graph by Euler. So this was like the birth of graph theory. So the island here, which was labeled W, becomes a vertex, and the area X, which is to the north, becomes a vertex, as does Y to the east and Z to the south. And you can see that you can go from W to X using two bridges. So that's where these two edges arise. You can go from X to Y over this bridge, from Y to Z over this bridge, and from Z, there's two bridges back to the island, and that gives rise to those edges in the graph. And Euler in 1736 solved this problem. In particular, what he realized is that in general, if you want what is now called an Euler circuit to start somewhere and return back, that every vertex in the corresponding graph has to have even degree, or there can be two odd degree vertices and the rest even degree, and you would start at one odd degree vertex and end up at the other odd degree vertex. Now, our project is related to this in the sense that we're looking at a different problem, but modeled in the same way, where we're interested in, we have a graph that represents, say, a network topology, and we're interested in gathering metrics on all of the links in the graph and possibly even vertices in the graph, so that we can get what's called the telemetry of the network. Now, I'm going to simplify this graph a little bit for an example. So I'm just going to turn it into a simple graph. So this is not a simple graph because there's two edges between W and X, and two edges between W and Z. So that's actually a multi-edge. So I'm just going to simplify this and number the vertices instead of labeling them with letters. Okay. So let's suppose this is our graph. Now, the algorithm in the project description has several steps. And the first step is to find the odd degree vertices. So essentially what we're going to do is, if the graph that we're given has odd degree vertices, And in this case, our graph does. We're going to transform the graph into a graph where all of the vertices have even degree. So in this case, we can see that vertex 1 has degree 3. Vertex 2 has degree 2, so that's even. 3 has degree 3, and 4 has degree 2. So we've got 2 odd degree vertices. All right, so that's what we find first. And the second step says to use the Floyd-Warshall algorithm to find the length of the shortest path in the graph between each pair of vertices in this set O. So we call it O for odd. So we can run Floyd-Warshall. We can do it on, we need to do it in the original graph G. So if this was our graph G, it just makes sense to run it in the algorithm in this graph because these vertices might be far apart, and we're interested in how do we get from each vertex in this set to every other vertex in this set, but in the original graph G, because we will need that information later. Okay, so in this case, it's a tiny graph. So we have 4 vertices, and we can just do this directly. Of course, you should implement the algorithm, but we can see that I have a direct edge between 1, 3, and 4. So assuming the distances of 1 are all given, I can get from 1 to all others at a cost of 1. Now, 2 has an edge to 1 and 3, but not to 4. So I have a path to 4 through 1 and also through 3 of length 2. And from 3, I can get to every other vertex at a cost of 1. And from 4, it's only to 2 that it costs me 2 units. Now, I'm really only interested in the vertices 1 and 3. And so I'm just going to look at vertices 1 and 3. So from 1 to 3, it costs 1. And from 3 to 1, it costs 1. So this, of course, is a tiny little example, but this tells us that the cost of going from 1 to 3 in this original graph G can be done at a cost of 1. Okay, so that will be information that we're going to need to use. Now, the next step of the algorithm says that we should find a perfect matching among the vertices, the odd degree vertices. So, and we should use a greedy algorithm. So we want to find a perfect matching. Now, so it's important that we're using a greedy approach because a greedy approach to do this optimally in general is expensive. So by using a greedy algorithm, we can find what's called a perfect matching, but it might not be the what's called the minimum perfect matching, or maximum, depending on your problem. In our case, it's minimum because we would be interested in shortest paths, but again, we're not finding a perfect matching optimally. We're just using a greedy algorithm. So a matching is nothing more than, once we've chosen an edge, then we couldn't choose any other edge whose endpoint is already in the matching. So for example, if I chose this edge between 1 and 2, I would not be able to choose this edge between 1 and 3 because it has a common endpoint of 1. So that one is out. I can't choose this edge for the same reason. But for example, I could choose this edge 4, 3 because its endpoints are disjoint from the endpoints of this other edge. So I could choose those two edges, and those would be the only two I could choose if I chose the one between 1 and 2 first, because I can't add in this edge between 2 and 3 because it's incident with this edge and also this edge. So either the perfect matching has these two edges, or it has these two edges, depending on which ones get selected first. Now, we're not actually selecting a matching in this graph, our original graph G. We're actually selecting a perfect matching only in a fully connected graph on these vertices in O. So if I look at the vertices 1 and 3, which are the vertices in O, and connect them in all possible ways, well, there's only one way to connect them. So I'm going to call this graph G prime. And so in fact, I'm looking for matching in G prime. Well, G prime only has one edge. So when I select it, I'm actually done. So in this case, my perfect matching is just the edge 1, 3. Okay, so the next step of the algorithm says, for each edge in the matching, add the edge into the original graph G with a weight equal to its shortest path. Okay, so I only have one edge in my perfect matching. So the algorithm says add an edge into the graph. So at this point, I could change the graph from what's called a simple graph, so in other words, no multi-edges, into a graph that now does have the possibility to have multi-edges. Now this one has shortest path of 1, as we saw here, which is just a subset of the results of Floyd-Warshall, just focused in on those vertices in O. Okay, so I add the edge into the graph. Actually, in the project description, it also colors the odd degree vertices red, so I can do that as well. Okay, now there's only one edge in my matching, so only one edge gets added into G. Now this is called a virtual edge. And when you're maintaining the adjacency lists, you should add these virtual edges into the lists, which are being maintained in lexicographic order, add it after, so in this case, because I have an original edge between 1 and 3, the virtual edge should get added after the original edge. So you'll have two edges between 1 and 3. The first one in the adjacency list will be the original edge, and the second one will be the virtual edge. So I also suggest you might want to mark an edge as an original edge and a virtual edge, so that you know which are edges originally given to you and which are virtual and got inserted into the graph by following these steps. Okay, now the algorithm says, so once we've inserted all the edges in the matching into the graph, and it will have a weight equal to the shortest path distance in the original graph, which in this case is just 1. So now the algorithm says, find an Euler circuit. And the instructions in the project description say that we're going to start at vertex 1. Now, the reason we're going to start at vertex 1, and the reason we're going to always traverse edges in lexicographic order, is so that we will all generate the same unique output. I mean, you could really start at any vertex, but of course, if you did that, then one person would get a different answer and another would get yet another answer. And we just want all of the answers to be the same, so that when we configure Gradescope, we can match the output on Gradescope. Okay, so actually I'm going to give myself a little more room here. Okay. Okay, so to build the Euler circuit, what you need is a stack. So I'm going to have a stack, and the top of my stack is going to be, so that my stack is going to grow to the right here. Okay, so the top of the stack will be the rightmost element. And then I have the circuit itself, the Euler circuit that's getting generated. Okay, well, if I start at vertex 1, and I'm told to select edges in lexicographic order, then the first edge I'll select is this one between 1 and 2. So I'm going to stack edge 1, 2 onto the stack. That takes me to vertex 2. Now vertex 2, so each edge is only gets selected once. So even though the edge 2, 1 comes before the edge 2, 2, 3 in lexicographic order, I've already selected edge 1, 2, and so the edge I will select at vertex 2 is 2, 3. Okay, so I'll just put a little hash mark on the edge to indicate we've selected it. Now at vertex 3, we can see the edge from 3 to 2 already has been used. So I have edges 3, 1 and 3, 4. Well, I should choose the edge 3, 1, and I should choose the original edge first. So the edge 3, 1, because remember, the virtual edge is added into the adjacency list after. So I would choose the original edge 3 to 1 first. That takes me back to vertex 1. Well, I actually do have two more vertices, or two more edges, I'm sorry, that I can take from vertex 1. And 1, 3 becomes before 1, 4. But if I choose 1, 3, notice it's a virtual edge. So I'm just going to use red to indicate that. I'm back at vertex 3. And I only have one edge I can select at this point. It is the edge from 3 to 4. And when I get to vertex 4, I only have one edge I can select, and that's the edge from 4 to 1. Now, when I'm at vertex 1, you can see that now all of the edges have in fact been selected. So now I can start popping things from my stack. And when I pop them, I'm going to reverse the edge. So I pop this edge 1, 4 and add it onto the circuit. So 1, 4. So now that's been popped. Pop the next edge. So that backs me up to 4. But notice there aren't more edges for me to traverse. So there's nothing left for me to explore from vertex 4. So I pop the next edge, reverse it. So 4, 3. So that returns me to 3. In this case, again, all edges have been explored. If there were edges that hadn't been explored yet, I would follow them and push them onto the stack. But in this case, there aren't any. So I pop 3, 1. Now, actually, whenever I pop, sorry, my red pen is not working well. Let's get another one. So when I pop this virtual edge, in this case, it's easy because the virtual edge only has length 1. The distance, the shortest path length is 1. And so it's in fact a direct edge. But again, if this virtual edge, it could have corresponded to multiple hops through the original graph. And if it does, then when I pop a virtual edge, what I would actually output in the circuit is the path that corresponds to that virtual edge in the original graph. So an example of that is done in the project description itself, but I'm just doing a smaller example for simplicity. Okay, so I pop that edge, and that takes me to vertex 1. At vertex 1, again, I've explored all the edges. So for example, I don't have another vertex off to the left here for me to continue exploring. If I did, I would take it and push things onto the stack, but they don't exist. So that means I pop the next element, which is reverse it, and I get 1, 3. So I'm back at 3. And at vertex 3, again, all of the edges have been used, so nothing else to do. So I pop the next edge, reverse it, 3, 2, takes me to vertex 2. Again, all edges have been followed. So I pop the edge, reverse it to 1, empty out the stack, and I'm finished. So what does, if now we should be able to follow the circuit and see that, in fact, I can get back, start at vertex 1, come back to vertex 2, and actually traverse every edge in the graph. Now, because we're introducing these virtual edges, it is possible that some of the edges in the original graph could get traversed more than once. That's actually correct. That's to be expected when using this algorithm, because after all, we introduced these virtual edges as a mechanism to turn the graph into a graph where all vertices have even degree. Okay, now in this little example, when I follow the circuit, we're going to see that, well, actually, let's try it. So the circuit says go from 1 to 4. So I go from 1 to 4, from 4 to 3, 3 to 1, then I have to go back to 3. So in the original graph, this edge gets traversed twice. Then from 3 to 2, and then from 2 to 1. So in fact, in this example even, you can see that the original edge between 1 and 3 gets traversed twice in order to find, well, it's actually now technically not called a Euler circuit anymore, because an Euler circuit can only exist in the graph if it really did have even degree, all vertices. But we had to introduce an extra edge in this case to make that happen. Okay, well, that is the whole idea behind Project 3. And the project description describes the algorithm on a bigger graph and shows you a more complicated example of virtual edges. So in that example, there are 3 virtual edges, and one of the virtual edges has a path that's of length 3. So it's more interesting because when you pop that virtual edge, you actually have to insert 3 edges into the circuit itself that correspond to that virtual edge. Okay, well, in this project, you get to design how you're going to represent things like, how are you going to keep track of a virtual edge versus an original edge? How are you going to actually compute the path between vertices in the set O? I mean, we can use Floyd-Warshall to find the length of the path, but how about the path itself? Well, we know Dijkstra's can keep track of the path. Can you modify Floyd-Warshall to actually keep path information as well? What kind of data structures are going to use? So the one requirement is that you use adjacency lists, but you might want to keep a parallel array that keeps track of the degrees of the vertices. For virtual edges, you might want to store paths. So you have to think about some of these design and think about and make design decisions and keep track of these decisions you make, because you're going to need to explain them as part of your submission. Okay, well, I just wanted to overview the algorithm I think if you should also read the trace of the larger example, both of these will be provided as some sample input for you. And then you can compare to the sample output among other output sets. Okay, well, that's it. Thank you.